Great. Welcome, everyone, to our first seminar series talk of the semester for the Design++ seminar series. I think we'll just jump right into it today, and I'm happy to welcome Olga Vysotska as our first speaker in our seminar series. Yes, so just to briefly introduce Olga. She is the first Design++ postdoctoral fellow in our fellowship program, which was enabled by our strategic partnership with Halter AG. And one thing so this talk in particular is the concluding research results of her fellowship. So very happy to see the body of work that is developed in this time. And yes, so during her fellowship, she worked with two different faculty from the Robotics Systems Lab and the Computer Vision Lab, Computer Vision and Geometry Lab. So she brings together robotics and computer vision. And one thing which I will not forget and has continued from the first time we met Olga in the beginning, she was very excited about tasks, localization tasks for messy environments, so really challenging, especially difficult environments. And I think this is actually really nice to see that, in fact, as mentioned previously this week, that this work, she would not have otherwise worked on construction sites without this fellowship. So I think this is actually a really, to me, a nice signal that we're moving in unique territory. So thank you very much for your work and looking forward to hearing your talk. Thanks, Olga.
Thank you, Daniel, for the introduction. Daniel actually said everything I wanted to say about the slide, but I'll just say that, I'm Olga, and I'm really honored to be here and tell you a little bit about the work I have done in 2 years. And maybe it's a bit different to other talks that they are in Design++ series, but I hope you'll enjoy and feel free to ask questions at any point in time. So as Daniel said, I have background in robotics and computer vision, and when I just pitched my idea here to Design++, I imagined how construction looks like from inside and what are the robotics systems that are there. But within these 2 years, I realized that when I say robotics, different people understand different things. So basically, to clarify, typically if you say robotics, people can imagine the different kinds of robots, for example, the one that lays bricks, or the ones that perform welding on site, or maybe you have heard about Hilti company. They actually provide their own robots for drilling in the inside of the environments. Or robotics can also stand for excavators or other heavy machinery that helps to do tasks of digging and grading and preparing the site before the construction starts. For me, robotics was always about this guy here on the left corner. So it's a robotics platform. It's much smaller than any other. It's basically like this. It has 4 legs, and it can navigate itself basically like a small or maybe medium-sized dog. And the benefit of this kind of platform is that it's mobile, it's way smaller than others, so it can actually fit into a building that's being under construction, and it doesn't need to be carried or transported with the crane or some additional materials to operate in the environment. So what can such a platform help with in the construction site? So what we looked at is the problem of documentation, the problem of documenting the state of the construction site. And as with robotics, when I say documentation, people can imagine a lot of different things. It can be documenting the processes, it could be documenting the design designs of the build. It can be how teams communicate in between each other. But just to narrow the scope here, when I'm saying documenting the site, or when I'm looking at this problem, I'm saying that we're going to capture the physical state of the construction site in a digital form. For example, we're going to scan the environment with the LiDAR scanner or maybe a camera and basically have a snapshot of the state of the construction site where we are going to go with this robot. And then the benefits that this kind of capture or this kind of snapshot will give to us is that you would have a digital model of that site, and you can zoom into this and examine it on your machine, on your computer, even without being at the site itself. The current state of the art for this digitalization or documentation services is actually that there are companies that provide digitalization services for you. It's typically especially educated or taught people how to use these devices. And as you might see here, it's either something more stationary, like a 360 RTC, or some device that you carry on yourself, or some device that you carry in your hand, like a handheld device. But in all of these cases, it assumes that the person is going around the site. The scalability of this approach is not too big because it should actually be a person that goes around, and most of the movement that people are doing is just carrying it around here and there. So basically, go here, go there, go here, go there. It's mostly, let's put this, time-consuming and not really interesting work to do. Moreover, depending on the size of your site, it can be quite time-consuming as also costly, since the companies charge per square meter that they scan for you. And hence, this operation can be performed quite rarely. So you wouldn't be doing this operation every week. So how can the robotics help with this problem? Well, the idea is that we will have a robot that will be equipped with the same or very similar setup, with the LiDAR and the camera, for example. And then the current state of the technology for robotics like platform like this is quite advanced in terms that they can locomote, meaning walk by themselves quite robustly, also in the environments like construction site. And they have no troubles, and we already saw it, almost no troubles traversing any part of the construction already. And robots are very good and very suited platforms for simple, routine, tedious tasks that otherwise could be very time-consuming for specialists. Robots can also operate on any given schedule. It can be every week, every day, every second day, at night, during the day, and so on. So while robots would be on the construction side, they could gather something which I call, and other people call, a digital twin. In this case, for example, reach a geometrically accurate point cloud. And then this point cloud could further be inspected by a construction manager or site manager, let's put it this way, even by not being physically at that location at that construction site. And this can be performed quite often. So the idea is that robots do this accurate digital twins for us. And then we also have, at least in my title, but also I hope you have heard, that exists certain device we call it AR device. I typically called here, consider here the AR glasses, but it also can be a tablet or phone with the AR capabilities. And typically, the sensors, they don't have these devices. They don't have a LiDAR scanner, which allows for us to get the highly accurate reconstruction, but rather they have lightweight cameras And typically these cameras look like this. So in theory, this device could also be used for providing the digital twins, but then we would need to make sure we walk in a specific patterns and actually examine all parts of the environment, such that we basically cover every space in the construction. And actually, I tried this for a couple of times. It's very annoying, and after a certain point in time, you start getting nauseous by walking like this and trying to figure out if you covered the whole space or not. So the idea here is that let's outsource the digital twin collection for the robots and use AR devices for either manual annotations or helping people to add additional information to the digital twin. Another point is that AR devices typically have the hand recognition. So it's not just that we can scan the environment, but also the construction worker, for example, can say, oh, there is something wrong over there in that particular part of the environment, pointing that out. And this information, in the best case, should be directly linked to a digital model. With the AR device, we also should be able to, for example, preview our digital model from, for example, a BIM information to say, oh, you know, there's something wrong because something is not built the way it was planned. And the idea here is that all of these worlds, robotics, AR, and construction world, they need to coexist together. So for this information to be instantly available in a digital world, all of these worlds should be basically aligned together. And they should be in the same, in other words, should be in the same coordinate system. So the idea of this work is we can achieve this alignment through the process called localization. We can localize AR world into the BIM world, robotics world into AR world through this process. And also recently realized that localization is used in the apps to basically translate the content of the apps to the other to the country they're shown in. So just to clarify what I mean by localization, in this case is the process of estimating a location of an agent. It could be a robot or an augmented reality device with respect to the world. And in our case, I'm looking either with respect to a digital twin, in this case, a high-resolution point cloud, or a BIM model. So the localization of today or of a year ago is a process that performs well in everyday scenes. For example, you can see here the living room or the ETH. So the localization already performs well there because those are feature-rich, how we call them, meaning that there are different colors, there are different objects, there are different gradients. Just looking at that image, the ETH building itself is quite a unique place. So for this environment, the localization will work well. And for outdoors, particularly GPS may not give you millimeter precision, but will roughly put you in the correct location anyway. The problem with the construction side that it's a different environment. It's what we call feature poor, meaning that when you are in the building under construction, everything is gray. All the walls look the same, especially if you're in a building which has like multiple floors with the same apartment layout. It's identical, and it's not so easy to say where you are at just having the snapshot of the environment. That's repetitive and highly dynamic. In this case means that you might see on one day a material or a scaffolding on one floor, but then it gets moved to another floor. But from the picture, it doesn't tell you that this is the same place or the place has changed. So the idea is, how can we augment the localization algorithms such that they perform better on the construction side? So my pitch was that we can use not just one single snapshot for the processing, but rather a sequence of data. Since robots and also AR devices, they don't just take one image and that's it, they don't process anything further, but while you move, they can collect a video or a stream of images, And while having this sequential information, taking it into account, this should make the localization better, as well as not just we want to make it better, but we also want to link the robotics world to the digital world of the construction side. So we also would like to incorporate the so-called background knowledge, in this case the BIM model, into making the localization itself more robust. And maybe to motivate a bit why this sequence approach makes sense. So here's, for example, three pictures of a place. And just by having this single information, would you be able to tell if it's the same place in the environment or not? What do you think? Shout out. Same? Is the same? Any other ideas? Yeah. Maybe it was taken in the evening. It's different. So it took you some, it actually indeed are different, and you might spot that on the left one, there is no wall there, and there's two walls, like the wall near the door here. I'll show you here. So this one, there's no wall, and here's the wall here. But if you just, from the robotics perspective, it will not look at individual concrete dots if you meant it that way. Or this, for example, this patch might seem different, but that would actually look at the same place. But if we put this information into a context that we start from one floor, and then we were going around on the second floor, and even though it was the same point in time, the lighting condition changed due to the properties of the cameras. There you can easily say that, oh no, it's all three different places. So what does this practically mean? So how could such a system look like with the robots being able to use sequence information as well as localize with respect to a BIM model? So here's a simple sketch. We have a robot, and it's equipped with a LiDAR scanner. That typically, when we talk about LiDAR scanner, it's a scanner that sweeps the LiDAR beam, and for robotics application, they're typically quite sparse. So that would something that we would call a LiDAR point cloud. And then we also assume that we have a BIM model. And having this inputs, we say we perform LiDAR localization against BIM model. What does it say? It means that we take this scan and try to place it correctly within the BIM model. Once we do it, we know exactly how these worlds are aligned. I also mentioned before that not just we have a LiDAR scanner on the robot, but we also can have cameras which are also placed there. Once we have this, we know and we can calibrate these devices with respect to each other. So we know exactly the relationship from the camera to the LiDAR, so how they are positioned. While we're collecting the LiDAR scans, we can also collect the sequence of images. And since we know exactly the relative transformation between images and LiDAR, we automatically would get the localization of camera with respect to this BIM model just by placing it there. And then the idea is that at some other point in time, the construction worker wearing or having the AR device will be going through the environment and collecting the image stream. While matching this newer image stream with the previous image stream, we are able to position the images with respect to our older robot ones. And once we do this, we get our localization of AR device with respect to the LiDAR, hence with respect to the BIM model. So that's the idea. And how did we test it? So basically, we took a robot to a construction site, which was provided to us in the collaboration with Halter company. We also collected the digital twin in form of a point cloud here beforehand. And what we try to do is to figure out if this localization is going to work. And in the end, what you see here is is basically where the robot was walking. This is from sensor point of view of the robot. The green one is the LiDAR point cloud from which has been collected by the robot. You can see extra people here, which are not in the model before. In this case, the localization is performing well. And how can you see that? It's because for example, these columns here are nicely aligned, the green lines on the columns are nicely aligned to the columns of the point cloud. And as well as other walls are aligned to walls. After we perform this localization, we can see what are the individual locations of the robot at every point in time with respect to the digital twin in this case. That's about the robot localization, and also said that we did something with AR and cameras. So what we did while the robot was collecting the LiDAR point clouds, also collected the footage from the front-facing camera. You might see here that it has quite a big field of view. The color palette, let's put it this way, is a bit brighter. I think it was earlier in the morning, and now the robot takes this particular trajectory. So this was in December 2024, and then we went back to the same location, but now with the AR device. And if you might have noticed, there is some other objects which are not present in the previous model. Their lighting conditions are different. Now we have some other dynamic things that were put there because of the material that needs to be used for construction. As well as we have now water here, which is not the best for localization because we now have light stripes, not just on top, but also on the bottom. So this confuses typically the system that it might be not the same place. And even worse than that, here is the wall that was constructed that was not there before, and actually our robot was passing there before 3 months ago. So all of these things contribute to the challenging part of the localization with respect to a different time frame. And as the part of this fellowship, we investigated what could be the algorithm that matches these image sequences robustly, such that we know that the query image in this case corresponds to the reference image exactly, or exactly as close as possible. And this was published on ICRA, is a big international conference for robotics, and got attention that we are working with the construction data, which is highly challenging, as reviewers pointed out. So that was a good sign for recognition. After we matched these images, we're able to also now place the positions of the camera, this gray pyramids. This is how we typically denote where the cameras were while we were collecting the data. With respect to this small coordinate system is the positions of the robot from the LiDAR. And as you might see that they are quite, if you remember the image streams, they're quite well aligned. Also the quick check is that I was wearing the glasses, meaning that this is my height and the robot is like this, the camera is on the robot there. So it definitely has a different height profile here. Right. So this was the localization with respect to a digital twin or dense point cloud. But what about BIM? I was talking about BIM all the time. So what we did here is we took a BIM model, which was also provided to us by our strategic partner for that particular construction site, which was very helpful. And what we did is we say, okay, let's reduce the problem of localizing to BIM to something that we already know, localizing into a point cloud. So in this case, we took the geometry information only from the BIM model, so nothing else, and rendered a point cloud that represents this place. The particular part to it that the BIM, and after that we performed the localization on this type of data. And since it's by definition is the same point cloud or the same concept of point cloud, it was expectedly performing on the level of previous approach. Maybe I'll stop here and show. So here you could see these green lines. They're here. They're here. That typically means that the LiDAR had hit the wall. And the problem here is that there's no green lines here, meaning that actually the BIM model represents the environment which, the way it should have been constructed, like as the end result. But while the robot was there, this wall didn't exist, as also I have pointed out with the images before. So even in case that the environment has changes like this, we still are able to localize quite reliable in this kind of situation. And I also pointed out here, but exactly closer, that this is the wall that doesn't exist, and then robot goes, whoop, hits the wall, hides behind that. And for example, there's also dynamic object. There was a blue machine in the scans, but it is not in the BIM model itself, because BIM model cannot know that there was a material or machine standing there at that point in time. And just the same, since we can now localize with the LiDAR and can match image streams with respect to other image stream, we can just now project it and showcase that the augmented reality device was also placed correctly with respect to BIM coordinates. Right, so great, we have localized ourselves, we aligned those worlds. What I didn't mention here, that for this localization to work, we need to set the initial pose of the robot, which, for example, for inspection task is a reasonable assumption, where you can say, my robot always starts at the entrance of the building, or my robot always starts from the place where the battery of the robot is, or where the charging station is. But the question is, what happens if you don't know where you start, or something goes wrong while a robot is operating in the environment? So as a part of master thesis, we have explored how can we solve a so-called kidnapped robot problem. It means that it's starts its sensor and has no idea where it is with respect to those worlds, and nobody can tell him because the robot is somewhere in the other part of the construction site. So the idea here is that we looked at the approaches that, given one LiDAR scan, like a neural network, that will tell you roughly what are the hypotheses where the robot could be given this measurement. And I hope I also convinced you that sequence of measurements is always better than one single measurement. That's why we took another, like an extension to that work, where we say, okay, we don't just take one LiDAR snapshot anymore, but we take multiple, like a sequence of them into account. And here you can see that the black dots are the hypothesis where the robot could be. The red dot is the ground truth, where it should be. So, and the green one is the most likely position at every point in time. So the idea is that the red and the green circle should be overlapping all the times, but this is a quite challenging environment with a staircase, actually. Something that I showed you before, where at some point in time the robot loses a bit its position, but in a couple of observation, it gains it again. This is currently under submission too. So what else did we do? So it's nice that Design++ is sponsoring our research on this, but one person or a couple of people can only go so far. So what we also said, like, let's make the world see this challenging environment. And we also, with cooperation with Halter, have basically collected data on the construction site, and we open source this data already under this link. Everybody can go download it. So we provide there the footage from 3 different cameras, as well as 2 types of LiDARs of different density and different patterns, as well as legged odometry, basically how the robot was moving at that point in time, as well as ground truth, which is very important for people to do further research on. Right, so what I was telling you before, that we are localizing with respect to environment, it's either point cloud or a BIM model. Also, in the localization, we call it a map, how the map looks like. What we also looked into is what if we have a different kinds of map? Instead of we just have a geometric information of the environment, what if we have a map constructed as a semantic information of the environment? For example, in the form of so-called 3D scene graphs. A scene graph is basically a graph of objects where you know that you represent your environment by saying there is not just a space of 3 by 3 or 5 by 5 meters, but rather there's space where there is a table. The table stays on the floor. The table also stays with respect to a big screen. And that basically the intuition behind this, that when we as people enter the room, we don't really check first what is the geometric relationship of the walls with respect to the floors, but rather, there are tables, there is a camera, there is a carpet. I must be in an open space in ITA building. But if I would be entering a bathroom, for example, I was like, yeah, it's a completely different set of objects, which allows me to localize faster. So we tried to figure out if this kind of information is useful just for us or also for robotic system that also would be useful. And there are two papers. One was submitted and accepted, and one under submission. And the difference between them, that first considers only one snapshot, and the second one takes sequence information into account and checks if the sequence in this case is better. It makes us localize better than the previous one. So that's it about the localization. But the question for after my fellowship stays: so what's next? Is this enough? Can robots and AR devices go to a construction site and solve documentation? Well, the answer is not quite yet, because we just solved or approached solving the localization part. But what we didn't look at is how can the robots autonomously go into this environment. Because if there is a robot that's just been guided by a human how to go through the environment, it's almost the same as the person would do this collection themselves. So for the next part, I'm going to be looking into how to make this autonomous robotic construction site digitalization possible. And this project was funded by Swiss. Before we were taking this robot on the wheels and try to figure out if this is feasible or not. And we are also participating with physics department. Maybe you have seen, I think it's over there, the building is being constructed. HPQ, I think it's called. So we're very looking forward to test our systems to the digitalization process of that particular building. Right. So what I was telling you here is that during my fellowship, I looked into, checked what kind of systems and add-ons to the localization could make it more robust. Robot and augmented reality localization in real construction site. As well as we looked at what if something goes wrong? How do we recover the robot from this kind of situation to make it actually more real-world applicable? As well as open source data set. The work was, all the work that happened here was summarized in 6 papers that were contributed to robotics, computer vision, and machine learning communities. So we're trying to reach the broader set of people and engage them into working with the real construction site data. And the topic is actually quite hot and start being even more relevant in robotics. So we're able to get some funding for the further investigation of robots and augmented reality technology for the construction site. So at this point, I thank you for your attention, and also big thanks go to the people who actually contributed a lot to this work too. Those are including students and our partners from Halter Group. Thank you very much.
A very big thank you, Olga, for this this inspiring presentation. So thank you for sharing the comprehensive overview of your work. Before I jump in with questions, I would like to open it to the floor. Yep.
Thank you for the very clear presentation. It makes a lot of sense and it's super cool. I got a question about so if I understand correct, one major task is actually to capture this discrepancy between the real construction site and the document, the 3D model, right? And also you also showed a little bit this discrepancy also threw off your results a little bit. So what you want to capture is essentially like make the workflow less accurate, right? I'm wondering if there's some strategy of how to strike a balance or basically how to deal with it.
Yeah, thanks for the question. Yeah, the changes that occur, so in this work I'm looking at localization, so how to make sure that the robot knows where it is at every point in time despite the changes that has happened. But you're right, if I'm a customer of such a system, I would actually don't care if the robot is lost or not. I actually want to know if there are discrepancies between my model. So currently it's a little bit of a chicken and egg problem. So if there's a lot of changes and robot doesn't know where it is, the model will not be aligned with the BIM model, and then you can't really say if it's because the robot is not aligned or there's changes in the environment. But the more robust the system becomes, the better is our chances that localization works, the alignment works correctly, and there's a changes in the BIM model. The other way to approach this is that to expect that the changes are small. For example, the same as with this, if we do the routine data collections of the robot, we would expect that from day to day, it's not like 10 walls have been constructed. So that could help a lot. If we can localize with respect to BIM, but also with respect to our previous model from before. That would make it more stable. The other thing I heard, and correct me if I'm wrong here, that there is a thing called 4D BIM models, the one that I guess changed with the time. So if you know that today is October 16, so the planned construction should be with this in this state. But I only heard about this. Could be. Maybe there's rumors about it, or I understood it wrongly that when you plan, you can also say like, at this month we're planning that these 2 floors are there, but might be rumors.
That makes sense.
Other questions? Yes.
Hi, just a non-technical question. Just generally, I mean, how is it different compared to the industry's research, related research, or do you collaborate with some industry giants, or do you use some of their tools? I mean, I just want to have a general picture because it's very hot, obviously. It's very hot, and many giants, they put in multi-millions, right, for these talents to work for them and all that. Boston Dynamics, whatever, Figure and all that.
Right, so this work is done with collaboration with Halter. I would not call them, I don't know if they're giants or not, but there's a construction management company rather than the contractors themselves. Also, for our next work, so this one, this one. We are partnering not with a big company, but with a startup called River. This is actually their robot. And the idea is here that we as a research institution check out directions and possible solution to a problem, but we don't do like long tails of the problems. So that's basically something that would probably be outsourced to a startup like that to provide the services to bigger companies. To answer your question about Boston Dynamics, well, this one is not in cooperation with them, but maybe they're going to be super excited with the progress that we can showcase in 2 years. And
So do some startups say discuss with you on potential collaborations,
yes.
or it's like your research result is just published and make it public and they can use it for free? How does it work in general?
So the research is public and everybody can use it once it's
I
published.
should thank you for that, right?
I mean, currently the ETH and strategic partners of Design++ have invested in this research. Like in my postdoc fellowship, that's how this research got possible. But for example, this one, it says InnoSwiss funded project. InnoSwiss is a Swiss funding agency. So now we're also going to be country of Switzerland investing in our ideas of us collaborating with the startup, collaborating with a company that might be interested in this technology to show the feasibility of such a technology to be perfectionized and scaled afterwards. So this is how we approach this currently. But if you know any other giant companies that are interested in this kind of product, we are very happy to collaborate.
I do know because I invested into one of the Asian companies just focusing on construction site automation. So we do use robotics, but these guys are expensive, right? It's headed by a UCLA PhD and he hired many engineers and we paid a lot, you know. That's why I asked the question.
We can discuss this later, but there's always funding opportunity. And the labs I'm working with, so the RSL and CVG, we're always looking for investments into our research. So yeah, that would be nice.
Any other types of questions, or not any other questions? We can stay on this level, but. Great. So I think this actually more or less concludes our time that we have allocated for the talk and Q&A. We have a little something for you, Olga.
Oh,
so,
funding, more funding.
More funding, yeah. That you have nicely acquired for yourself in the next step. So we do have a tradition of giving the Design++ bag. Inside you'll find something in addition.
Oh my God,
as a thank you. And this is from all of us for your excellent work and congratulations in finishing the fellowship and also as our first. So thank you very much.
Thank you very much, guys. This is so nice of you. First you sponsor me. First you sponsor me, and now you give me presents. Oh. I would recommend everybody to apply for the fellowship. But thanks for the opportunity too. I think it's opened a lot of interest actually on once people see the data, like, oh, it's really, really challenging. We should work on this. So I think it's thanks for the opportunity.
Yep. Yeah.
Thank you very much.
And so we have an upper row, which is actually on the other side of the staircase, so you can see it over there. Thanks.
Okay,
and we have our next talk on the 30th of October. So we hope to see you there. Molly Claypool will be speaking from bits to buildings, micro factories for housing. So I hope to see you also there. Thanks again.